Hello, thanks for joining me as we finish off Unit 7, our Chemical Equilibria unit. To finish off today, we're looking at the concept of Ionic equilibria and the Brønsted-Lowry acid-base theory, where our lesson objective is to understand the Brønsted-Lowry theory of acids and bases, describe how the strength and concentration of acids and bases affect pH, and the final two learning outcomes that we'll be addressing from this unit. So, we've looked quite a bit of detail at what an equilibrium is, forward, backward reactions, same rate when they reach that equilibrium. We're now going to apply that to the concept of acids and bases, right? So these are two words that I'm sure that you've heard at some point floating around. So let's just consider what an acid is. An acid is a substance that neutralizes a base to form salt and water. So our classic acid-base reaction, we have an acid, we react that with a base, we form an ionic salt and water. So we can define an acid this way, as something that reacts with a base to form salt and water. Similarly, we can define a base as something that reacts with an acid to form salt and water. But if we look at a bunch of acids that we have over here, I've just listed some: hydrochloric acid, sulfuric acid, nitric acid, ethanoic acid. Let's have a look what they all have in common. What is common between all of these acids is they have a hydrogen atom. And this is one way that we can define what an acid or a base is, by defining how this hydrogen ion, this hydrogen atom that ionizes once it's dissolved, or once it's in solution, I should say, how that moves between the two. So let's consider this idea of acids ionizing water. If I have something like hydrochloric acid, so I'm going to get rid of my general reaction here. Let's think about if I've got hydrochloric acid, HCl, and I have that in an aqueous solution. I have that in water. What happens is it will ionize into a H plus ion and a Cl minus ion. What other examples do we have here? We've got something like nitric acid. If we think about nitric acid ionizing water, I'll have HNO3, and then I put that in solution, in an aqueous solution, I'll end up with a H plus and an NO3 minus. So we have this hydrogen ion that is common to all acids that we're going to look at. Now, if we think about this hydrogen ion, a hydrogen atom has one proton and one electron. So if this is ionizing, it's losing that one electron. So really, this hydrogen ion is just a single proton. So we're going to use hydrogen ion and proton interchangeably when we're talking about the movement of this species. So we have some bases dissolve in water to form hydroxides, for example, sodium hydroxide. So the same way that we could define an acid as dissolving to have H+, we can define bases as having OH-. So we could have sodium hydroxide in an aqueous solution dissociating to form OH-. But we're not too concerned about this. We're going to really focus on the H+ and how the H+ behaves. And then just the final bit of vocabulary to make sure that we're aware of. Base and alkali, they refer to two different things. So a water-soluble base is called an alkali. So all alkali are bases, but not all bases are alkali. Has to be water soluble in order to be called an alkali. Excellent. So let's get this definition, Brønsted-Lowry, that we mentioned at the title of the episode. The Brønsted-Lowry theory of acids and bases. Acids are proton donors, bases are simply proton acceptors. It was devised by two scientists independently of each other. A fella from Denmark, a Danish fella called Johan Nicolai Brønsted, and an English lad, physical chemist Thomas Martin Lowry. So name dropping both those fellas. All right, so we can look at it with this general equation here, which I'm going to rewrite up on the whiteboard. So we have some sort of acid. I got HA. Where's my red pen? A isn't a chemical symbol. A is standing for acid. And I'm showing here that I have the proton that can be donated from the acid there. Then we have a base. Where'd my black marker go? Plus B, again, not an actual chemical symbol, B is standing for base. Now, this has to have some source of electrons, because if we're losing a hydrogen ion here, and if we're gaining a hydrogen ion over here by that Brønsted-Lowry definition, then it's got to form some sort of covalent bond. As the hydrogen is just a single proton with no electrons at all, just a single proton, the electron source has to come from the base. So it could be a species that has a lone pair of electrons, could be a species with a negative charge, however, it needs to have electrons available to be bonded with it. Then we reach an equilibrium, because we're in the equilibrium unit. We're going to look at this idea of acid-base equilibria. And then what happens here? We've now got a neutral species that has lost a proton, the single proton from the hydrogen, so it's going to be a proton down. So we're going to end up with an anion here, and then it's keeping the electrons from this electron pair there, because again, our hydrogen is just a proton. So we're going to end up with a minus charge there, and then we're going to end up with a species over here that now has a, what do I want to do here? H with a blue B, like that. And this is going to end up with a positive charge in this situation. Excellent. So this is just a situation where we've got two neutral species on this side and an ion on this side each. It could end up that we had 9 on that side and 9 on this side. This is just one general type equation. But you can see we've got an acid. So this is my acid. This is donating the hydrogen. It's losing the hydrogen and donating it to the base, which is the hydrogen ion acceptor. And we end up with that. Okay, let's keep looking at this in a bit more detail. Let's consider the backward reaction in an acid-base equilibrium. So if I just consider this as a forward reaction like that, let's look at the backward reaction. So in the backward reaction, actually I'll keep that, we're going to have the A minus there, and then we're going to have plus, we're going to have the HB like this. So I'm just doing the backward reaction here, and this is forming the species over on this side, which is a HA plus a B. So if we think about this backward reaction, we end up with a species here, which is accepting a proton. So in the backward reaction, this would be a base. And then we got this species here, which is now the species that's donating the hydrogen. So this species here would end up as the acid. So we get quite an interesting thing where when we have a acid-base reaction at equilibria, the species that was the acid, once it's donated the hydrogen ion, now becomes the base. Yeah, and that makes sense, because if it could have had a hydrogen over here and it's lost that, well, of course it can accept the hydrogen over there again because it had it there to begin with. And then we ended up with the opposite of that. So the thing that ended up with the base, after it's now accepted the acid, it has now turned into an acidic species itself, because this could then donate that hydrogen. So we end up with this terminology to refer to these types of species. So the species that was now the acid is now acting as a base. So that's this species was an acid on this side because it can donate a proton. However, now on this side, it is now able to accept the proton. The species that was the base is now acting as the acid for the same reason. So we refer to these as conjugate pairs. Conjugate is just a word that means that they're connected in some manner. So they're sort of pairs, yeah? So if we look here, we have the acid there, we have the base there. The species that was the acid has now turned into a base, so we refer to that as the conjugate base. So this is the conjugate base of the acid. So this is the basic species once it's lost that acidic hydrogen. And then similarly, the thing that was the base is now the acid, so this is the conjugate acid of that base. Again, conjugate means that they're connected. So this was the species which is connected to that, and this is the species that was connected to that. So we can identify these as conjugate pairs of each other, where we have a definition that a conjugate pair is an acid and base on each side of an equilibrium equation that are related to each other by the difference of a proton. So we have our one conjugate pair here that are related by the difference of the proton, and our other conjugate pair there. All right, let's do an example with a real chemical equation. For the reaction below here, label the following: acid, base, conjugate base, and identify the conjugate pairs. If you would like to pause and have a go at that now, do that and check your answer now. So let's write out the question. We have ammonia, which is dissolved in water, and this reaches an equilibrium of ammonium ions, aqueous, and hydroxide ions, aqueous. So we're going to label the following. We've got to determine what is the acid and what is the base. Let's start with that. So the acid and the base are referring to the reactants. So we've got to see which one of these species is accepting the proton, which one is donating the proton. So NH3 is going to NH4. So this is accepting the proton, yeah? By our Brønsted-Lowry definition of an acid and a base, bases are the proton acceptors. So this one here is going to be the base. A base is a proton acceptor. An acid is a proton acceptor. So by the very definition of something in an acid-base reaction, if this is reacting with a base, it means it's an acid, because we had that definition before. But let's look at it in reference to its conjugate pair. So we have H2O over here, and we have just OH over there. So this is losing the hydrogen. It's a hydrogen donator. So it's donating the hydrogen to the base, which means by the Brønsted-Lowry definition, it is going to be an acid. Just something to just mention here very briefly is you can define things as different kinds of acids and bases. For example, you got a loose acid and base, which sort of looks at the electrons as opposed to the idea of the movement of the proton. So do be specific when you're referring to it. If I'm referring to a base and an acid here, I'm referring to a Brønsted-Lowry acid and a Brønsted-Lowry base. But we've only just introduced one definition, so don't worry too much about that, just like I say, just to be aware of it. Cool, so we've got our base and our acid. So that means that the thing that was the base, this is now an acidic species. This can now donate an acid. And if we look at this backwards reaction, that's what it's doing. This is then donating the hydrogen to that to get the reverse reaction. So if this was the base, this is now an acidic species. It's related to that species because it's related through the gaining of a proton. So this will be our conjugate acid. And then that will mean that this is our conjugate base. And then we've just got to identify the pairs. This is going to be one conjugate pair. This is going to be the other conjugate pair. Let's have a look. We have ammonia as the base, water as the acid, ammonium ion as the conjugate acid, and hydroxide ion as the conjugate base. We have one conjugate pair there, and we have another conjugate pair there as well. Excellent. Let's keep moving through. I don't think there's anything too intense there so far. Another bit of vocabulary that we are going to introduce, an amphoteric substance. Some substances are able to react as both an acid and as a base. So they are able to donate a proton, but they are also able to accept a proton. So they can do both things. This is what we refer to as an amphoteric substance. From the Greek meaning ampho, a lot of the times with all this chemistry vocabulary, it's useful to sort of break down the word and consider what that's saying about the word. So ampho is a Greek prefix meaning both sides, so it can be an acid and a base. I mean, if you think like an amphibian is a species that can go in both land and water, yeah, to live. So amphoteric can both accept a proton and donate a proton. Ampho, amphibian, amphoteric. Hopefully that helps you to remember it a little bit maybe. Consider water and the Brønsted-Lowry theory of acids and bases. So water and water going to H3O plus and OH minus. So in this instance, we have one hydrogen. Let's say this hydrogen is turning into that hydronium ion, and it's gaining a hydrogen, so it's acting as a base in that instance. But another water molecule, which is identical to that water molecule, this one is donating. So this one's going from H2O to OH minus. So we can see the water is acting as both an acid and a base. It is an amphoteric substance. All right, question. Here's a chance to have a go. Demonstrate water acting as an amphoteric substance through acid-base reactions with hydrochloric acid and ammonia. So write two reactions of hydrochloric acid with water and ammonia with water to show it acting as both an acid and a base. Pause to have a go and then check your answer. So, reactions with hydrochloric acid. So let's start first with HCl. Let's say that's in the gaseous form. And we're reacting it with some water. So we are bubbling it through water, which is in the liquid form. In this case, we are going to have, let's say, for now we'll put it as an equilibrium. We're going to address this in just a moment. So, hydrochloric acid is going to be the acid. There's a hint in the name. So this is going to donate the hydrogen ion to the water. So we're going to be ending up with Cl- ions and then H3O plus ions like that. The question didn't ask us to do this, but let's identify the conjugate pairs. So we have the acid and the conjugate base, and we have the base and the conjugate acid. What was the other one? Water reacting with ammonia. So in this case, we're going to have NH3, let's just say aqueous, plus water, liquid, equilibrium. Now in this case, this is going to be our base. So this one is able to accept the proton. So the higher H2O here, the hydrogen is going to be coming from this. So the water is acting as an acid here. So we're going to end up with ammonium ion, NH4 plus, aqueous, plus hydroxide ion, aqueous. So acting as the acid here, so we're going to end up with the acid and the conjugate base, and we're going to end up with the base and the conjugate acid. You beauty. Let's check that on the slides. One equation and two equations. Cool, that's what we have up here. But in the answer here, we don't have an equilibrium arrow. We've got just a regular reaction arrow. That has to do with strength, the acid strength. And we're going to look at how strength, concentration relate to this thing called pH. Now you've got to be careful here because our vocabulary is very specific. When we're referring about the strength of the acid and the concentration of the acid, we've got to make sure that we're referring to exactly what we mean. Yeah, so whereas we talk about something being strong or something being dilute or something being weak or something being concentrated, we can kind of use them maybe a little bit interchangeably. Here we can't. What do I mean by that? So when we're talking about strong and weak acids, this is referring to how much it dissociates in solution, therefore how much it ionizes. So it's referring to the position of the equilibrium. So if we have a strong acid, that means that we're making lots and lots of the ion. It ionizes a lot, yeah? So in a strong acid, we have equilibrium being pushed very far to the right-hand side. And in fact, for hydrochloric acid is such a strong acid that it's not really that much of a reversible process. It pretty much all ionizes. Whereas if we have a weaker acid, such as something like acetic acid or ethanoic acid, CH3COOH, if we were to ionize this in solution, we would only get a little bit of it being the ionized form. The majority would stay in the, I guess, the molecular form, you could say. And that would be what, H3O plus. Yeah, so when we're talking about a strong acid, we're saying it ionizes a lot. So equilibrium lies very far to the right-hand side. When we're talking about a weak acid, we're talking about an equilibrium lying to the left-hand side. What do we have written here? Notice the arrows in the previous example. Yep, talked about that. HCl is a strong acid. It almost completely dissociates in solution. So we get that, where it's pretty much all going to the ionized form. Equilibrium is very far to the right-hand side. Whereas our ethanoic acid is weak, it only partially dissociates. So we have an equilibrium that lies to the left-hand side, yeah? And then obviously this is the same for bases. If you're talking about bases, then it's just also the degree of ionization as well. So if strong base completely dissociates, weak base only partially dissociates. However, when we're talking about concentrated and dilute, this is referring to how much of the acid or base is in the solution, yeah? Concentration refers to the percentage of acid or base in an aqueous solution. So it's the amount per volume. So we've seen this equation before, so the number of moles per decimeter cubed, the amount of the acid or base per volume of it. So you can have all these different combinations. You could have a dilute strong acid, you could have a dilute weak acid, you could have a dilute strong base, you could have a concentrated weak base. Yeah, so they're all going to have different, I guess, the solutions are going to have different chemical properties depending. And how we measure this acidity or basicity is using something called the pH scale. So it's used to specify the acidity or basicity of an aqueous solution. pH denotes the potential of hydrogen, P for potential, H for hydrogen, and it's a measure of hydrogen ion concentration expressed as a logarithm to base 10. So we got this equation here where the pH is equal to the logarithm of the concentration of H plus ion. So the good news here is that we don't really need to understand sort of what a logarithm does. More mathematics thing, we just got to be able to find the button on the calculator, so that's good. But it just sort of makes the scale a bit more condensed, I suppose, might be the right way to put it. But we've just got to plug the numbers in if we have to calculate it at any point. All right, and we measure these things on what's called a pH scale. So a pH scale goes from 0 to 14, where 0 is as acidic as you can get, 14 is as basic as you can get, and 7 is neutral. So the closer to 7 you are, the weaker the acid. The closer to 7 you are, the weaker the base is. Yeah? So you can consider how pH would change with varying acid-base strengths and concentrations. So if you had a very strong acid, for example, that completely dissociates, but you only have a dilute, you only have a small amount of it in your volume of solution, then your pH would be less high, would be closer to 7 than if you had a concentrated strong acid where you would have more H+, where it would be further down towards 0. So you can see your pH of your solution, you could have, say, a weak base that's very concentrated, and that could have a similar pH to a very strong base that is very dilute. So the pH is only a measure to do with the concentration of H+. So depending on if your strength, depending on the concentration, the weakness, that's all going to affect the pH. And that concludes our Unit 7. What have we done? We've shown understanding of and used the Brønsted-Lowry theory of acids and bases, including the use of the conjugate acid, conjugate base, also sometimes called acid 1, base 1, acid 2, base 2 concept. That's just referring to the same conjugation that we looked at. And explain qualitatively the differences between strong and weak acids and bases and their pH values of the aqueous solutions in terms of the extent of dissociation. Task for this lesson: if you would like to consolidate your understandings, pause now, work through each column one at a time from the bottom up to the top. And that is the end of our chemical equilibria unit. Thanks as always. I will see you as we begin Unit 8 in the next video. Have a good day.